Hi there! Welcome to the 32nd episode of the Synth project, where we are building a synth together. Today we will work on another piece of the control voltage processor, the sample and hold component, one that is very powerful part of the toolbox of any synthesizer, either analog or digital. This component is able to take a sample of a control voltage based on a trigger and store the value so it can be used continuously, even after the original control voltage is gone. This opens a whole new set of possibilities in the sound generation. Let's get into this great subject without any further ado. From the perspective of the music player, the sample and hold component is a very simple one to use. We provide a variable control voltage at its input, then we send a pulse on the trigger input at the appropriate time, and the value of the control voltage at that very time gets stored into the device and presented on its output. At that point, the sample and hold device can provide that same value of control voltage for a relatively long time, until a new trigger is fired and a new value is selected. Let's see how this behavior can be achieved using analog electronics technology. Here is the schematic of the device. It is all built around a single integrated circuit containing 4 operational amplifiers. 3 of them are only used as buffers with a very high input impedance. The 4th instead handles the trigger signals. Let's start at the upper left of the schematic. Pin header P11 receives the input control voltage, which is passed to U4.1, which is the first of 4 low-noise JFET input op-amps. Such op-amps have a very high input impedance in the order of 10 to the power of 12, or 10 teraohms. We'll see in a moment why we need such a high impedance. U4.1 is connected in a voltage follower configuration, and so it basically takes the control voltage at the input and presents the same voltage at its output on pin 1, without loading the circuits that generated the control voltage itself. The output of U4.1 is connected to the source of an N-channel JFET set up to work as a switch. When the voltage at the gate of this JFET is negative enough, the signal at the source will be totally blocked. But if the voltage at the gate is positive, then we can find at the drain of the JFET the same voltage present at the source. The voltage at the gate depends on a voltage divider made up of resistor R19 and a second JFET, connected in such a way to behave like a variable resistor. When the signal at the gate and source of this second JFET is negative, thanks to resistor R19, the gate of the first JFET will be at a voltage of negative 12. In such conditions, the first JFET, Q1, will behave as an open switch, and we will have nothing at the drain. However, if the voltage at the gate and source of Q2 is positive, then the voltage at the gate of Q1 will also be positive, and Q1 will behave as a closed switch. In such condition, the signal at the source of Q1 will be presented as well at the drain pin and will quickly charge the capacitor C13. Then, once the voltage at the gate of Q2 becomes strongly negative again, Q1 will open. And at this point, capacitor C13 will find itself charged at a certain voltage and unable to discharge because of the high input impedance of U4.2 and the high output impedance of Q1. The voltage at capacitor C13, since it is given as input to another voltage follower, which is U4.2, will be available on pin 7, and therefore the output of the sample and hold device, and this until the voltage at the gate of Q2 changes again. But if the voltage at the gate of Q2 remains negative, then the output of P12 will keep holding the last value of voltage stored in the capacitor. Such value, given the size of C13 and the impedances of Q1 and U4.2, will remain practically unaltered for a very long time, relatively speaking. But how can we provide the appropriate voltage to the gate of Q2? The trick is to use a trigger signal coming from an external device. This signal is introduced into the trigger input P13 and applied to the non-inverting input of U4.3, configured as a voltage comparator. The reference voltage is given by the voltage divider made of R21 and R22, which brings a voltage of 2.55 volts to the inverting input of U4.3. If there is no trigger signal, or if P13 is not connected, the voltage at pin 10 of U4.3 will be lower than the one on pin 9. As a result, the output of the op-amp will provide a voltage of negative 12 volt, and therefore disabling Q2 and Q1. When a trigger impulse is introduced on P13, we will temporarily have a voltage greater than 2.55 volts on pin 10 of U4.3. As a result, pin 8 will be at a positive 12 volt and will cause Q2 to present a very low resistance, which will cause a positive voltage on Q1 gate, which will close, and C13 will charge or discharge, depending on the previous value, to the same voltage present at that moment on Q1 source, which is the control voltage at P11 at that very moment. Once the trigger impulse terminates, C13 will remain charged at that voltage value, which will then be presented at the output on P12. There are still two little details that we haven't addressed yet. The first one is the presence of U4.4, which will replicate the trigger signal at its output. That is done so we can still retrieve a copy of the trigger signal to do something else. The second detail is the switch SW1. When the switch is closed, regardless of what is present at pin 10 of U4.3, Q2 will have a positive control signal, and so it will have a very low resistance, and a positive voltage will also be available at the gate of Q1, forcing C13 to follow the voltage present on pin 1 of U4.1 continuously, and therefore disabling the sample and hold device. This may be useful while playing live, in the case we want to bypass the sample and hold device without the need to change the position of the patch cables on the synth panel. Let's now run a few tests in lab to make sure that everything works as expected. Here is our breadboard where we have already mounted the two previous circuits of the control voltage processor, the limitator and the mixer. I have added the sample and hold circuit on this same board in this area. This one is the IC containing the 4 op-amps with JFET input, the TL074. This is the capacitor used to memorize the control voltage sample. It is basically a film capacitor with very small internal losses, so it is supposed to hold the charge for a relatively long time without decreasing its voltage over time. This is the input of the device, and here is the output. This one is the trigger input, and this one is the trigger through. These are the two JFET in the circuit. This is the one that works as a variable resistor, and this other one is the one that works as a switch. I have already set my function generator to provide both a control voltage input and a periodic trigger signal. The control voltage is shaped as a sine wave, all positive and with a max amplitude of 10 volts. The other channel of the generator provides instead the trigger signal, set as a pulse with a duty cycle of 0.1% and a pulse amplitude of positive 10 volts at a frequency of 3.3 Hz. I have chosen such frequency to prevent correlations with the actual input signal, which I will later run at 1 Hz. This way, each trigger will sample a different value of the input signal. Let's now connect all the cables to the circuit. The trigger needs to be connected here, and the control voltage instead goes here. I will connect channel 1 of the oscilloscope with a yellow trace to the output of the sample and hold circuit. Channel 2 in blue is instead already connected to the input signal on the function generator, and so we can compare the samples with the actual signal. And here is the oscilloscope screen. Once again, this blue trace is the control voltage at the input of the sample and hold device. The yellow trace represents instead the output of the device. All the triggers happen at the moment you see the output changing suddenly, retaining the voltage of the input signal at that very moment. If I disable the sample and hold circuitry through the switch I added, the output signal will be identical to the input, since the JFET Q1 is always closed, and so the capacitor voltage follows the input continuously. When I open the switch, the circuit starts sampling again. At every trigger, the capacitor is charged at the same level of the input at that very moment, and then remains at that value until a new trigger is fired. Look at what happens when I change the frequency of the input signal. The circuit still grabs the instantaneous values at the moment of the trigger, and the output reflects those values until the next trigger is fired. If I instead reduce the frequency of the trigger, you can see how each sample remains constant for a longer period of time until a new trigger is fired. Note also how the voltage level of the output in these intervals practically does not change, thanks to the big value of the storage capacitor and the high impedance of the circuitry around the capacitor itself. So all in all, the sample and hold circuit seems to work exactly as expected, and so we can safely add it to the control voltage processor without any changes. However, to complete the whole module, we still need to add two more elements, the glide and the LED voltmeter. And those will be the subjects for the next two episodes of this series. To avoid missing these episodes and any other in the future, please remember to subscribe to the channel if you haven't done so already, and also make sure you have your notifications enabled. See you soon in the next video, and as usual, happy experiments!